All right, today we are going to start talking about the graphs of rational functions, and they are mainly the main features of these graphs are actually where they don't exist, where they're undefined. So there are three definitions to jot down um, to kind of define these three different ways in which our graph is undefined. So this first one, a point of discontinuity. In other words, this is going to be a hole. So a single point on the graph where the function is undefined. Then we're going to have something called the vertical asymptote, which is a vertical line that the graph approaches but never crosses. And then a horizontal asymptote, which is a horizontal line that the graph approaches but never crosses. So it's a lot easier to see where this stuff shows up if we actually look at a graph. So on the right side of your notes, you have this graph here with a rational function. And if you did our Explore activity, you would have seen that this is the general shape our rational function takes. We might have three different types of discontinuity. The first one that you guys wrote down was that point of discontinuity. And that will show up at a single spot along our graph where there is a kind of gap where our function is undefined. That is what we call a hole. All right, and we'll see how to find that algebraically in a little bit. That second one you got was that vertical asymptote. And if we look here along this blue dashed line, you'll notice that on both sides of my graph gets really, really close to it, this blue dashed line, but it never actually crosses it. It makes a jump from positive infinity to negative infinity if you're looking at it one way, or you can consider it vice versa, jumping from negative infinity to positive infinity. But this is what a vertical asymptote looks like. And that last one, you'll notice that we have a similar kind of thing happening horizontally, where there is a line that our graph never actually crosses. It approaches it on both sides, but it never actually crosses over. This is a horizontal asymptote. So we are going to start finding these, and it's going to be really important to have Desmos open alongside of this. You'll see me jumping back and forth all the time so we can kind of verify how this stuff works. We're actually going to start with vertical asymptotes because these are the easiest ones to find and they make the most sense. Vertical asymptotes will be located at x values where the denominator of the function is equal to 0. If I look at this first function here in example 1, we have the function of x equals 2 divided by x minus 3. And if we were to plug in the value of 3 here, f equals 3, we would get 2 divided by 3 minus 3, which is 2 divided by 0, and that is undefined at that spot. So what happens graphically if I go into Desmos and graph this, my f of x equals 2 divided by, and you can use that slash sign to get the fraction, x minus 3, you'll notice that, hey, at this spot of 3, at this line of 3, my graph never crosses that line there. And I can even toss in a line at x equals 3 to show you, hey, this blue line is where we are never, ever crossing. That's where our asymptote is. So we can just simply see this in the equation by, very similar to our polynomials, noticing that, all right, we have this factor in our denominator. If I can set x minus 3 equal to 0 or find the 0, I know I'm going to have an asymptote at x equals 3. Let's try this with two other equations here. So in example 2, we have the function of x equals 9 divided by x plus 1 times x minus 5. Based on inspection of our formula here, okay, and we're looking at the denominator, so just the denominator here, I have x plus 1 equals 5, which tells me I should have an asymptote at x equals negative 1. And I have x minus 5 as a factor. So I'm going to have an asymptote at x equals positive 5. let's check that out in Desmos and see if that works. So I'll clear my last one. We have the f of x equals, looks like 9 over x plus 1 times x minus 5. Let me double check, make sure I put that in correctly. Okay, you get a funky shape. But if we look and see, all right around the point -1, in the line -1, my graph goes up, it goes down, and same thing happens over here at 5. My graph goes up, it goes down, and never actually crosses that line. And again, we can kind of test these out. X equals -1, boom, we just graphed an asymptote. X equals 5, boom, we just graphed the asymptote. And if you scroll up forever, you'll notice that neither of these lines actually intersect. If you click on them, no gray dots appear. There is no intersection point. So let's try this on example 3. We have a few things happening here in our denominator and one up top in the numerator. The numerator we can completely ignore. X plus 3 isn't going to factor into this at all right now. We do have, with this x plus 6 factor, we're going to have an asymptote at x equals -6. With our x minus 2, we're going to have an asymptote at x equals +2. And this last one here is tricky, but also not. If we just have an x and it's not being added or subtracted by anything, the value that's going to make it 0 is simply 0. We're also going to have an asymptote at x equals 0. Now, let's put this into our Desmos, see what that looks like. Kind of clear some of my last stuff. So on top, we had x plus 3. On bottom, we have x times x minus 2 and x plus 6. And you'll notice that if I go to the point 3, if we just want to first look in the numerator, okay, 3 has nothing to do with it. There's no asymptote there. At -3, however, we do have a 0 in our graph. And that makes sense because if we plugged in -3 up top, we would get a 0 in our numerator. It would zero out our function. But if we kind of run left to right here, if I look at x, okay, there's an asymptote at 0. Okay, let me change that to a blue color there. Okay, so that works out. The other asymptote we had was x equals 2. You'll notice that that also is showing up there. We have that asymptote there. And x equals -6 is that third point of discontinuity. And you can tell by the equation that we just can find basically the zeros of the denominators. So in more complicated problems, when we don't have factored form, if I go back, notice how all of these examples we went through, 1, 2, and 3, we had everything in factored form. If we're not given factored form and we're given standard form, it becomes a lot more difficult to find. But we can actually use our Desmos and find these things without factoring first. We're simply going to just plug it in and inspect and guess and check to find these asymptotes. So this first function, let's plug it in. There is a lot going on with it, but just need to make sure we're paying attention to detail. We have our fraction. I'm going to set that up first. So negative x squared minus x plus 6 goes up top. And on bottom, we have x squared minus 12x plus 36 on the bottom. Now, this one's really funky, but if we kind of zoom around and look out here, it looks like there might be some sort of discontinuity in this maybe 5 to 10 range. So one thing, I'm going to start by guessing x equals 5. If I do that, it gives me a line that looks kind of somewhat close, but as I scroll down further, if I click on that line, you'll see we actually intersect there. So x equals 5 is not an asymptote. If I bump that over and say maybe, okay, x equals 6, okay, I can kind of scroll down there, and there it looks like if I scroll down forever, I'm never actually going to cross that line. Another way that we can tell, if I kind of home back in, is I have this function graphed. If I go to settings and click table here, okay, it will kind of auto assign a few values of x and plot those along our graph. Well, if I add another x value in this table and say, all right, give me the x value at 5. That was my first guess at the asymptote. You'll notice that it gives me a value back. But if I plug in an x value of 6, notice how that shows up as undefined. So therefore, we would have an asymptote at x equals 6. So our asymptote here is x equals 6 from the graph. I would go ahead and try this on your own real quick, and then come back and check it against mine. But we are going to do example 5 as well. So example 5, x squared minus 16. Let me go back. Let's go back and kind of clear our work here. So I'm going to set that fraction first by hitting the slash sign. We get x squared up minus 16 up top. And 3x squared minus 6x minus 24 is on bottom. I'm going to zoom out real quick, get an idea of what my graph looks like. It looks like we just have that one vertical asymptote. This one actually looks like it's a lot easier to see. If I kind of look up and down at this line, x equals -2, that looks pretty good for my vertical asymptote. Let me just throw that in and test it. And it looks up if I scroll up. It gets really close, but it never actually crosses if I zoom in there. And we can also test it with that table method too, where I hit settings, hit that table. And you'll notice in this case, it already gave me that point x equals -2, and it is undefined at that portion. So our asymptote is at x equals -2, and we found that from the graph. So the other instance of a discontinuity we're going to cover today is a hole, or a single point of discontinuity. So these are going to be located at x values where the denominator of the function is equal to 0 and that same factor exists in the numerator. So if we look here, example 6 is a really straightforward example. We should expect an asymptote at x equals 3, right? But if we throw this in our graph, which let's kind of delete some stuff, we have x, oh, got to delete a lot more than that. We have x minus 3 up top and x minus 3 on the bottom. You'll notice that we basically have what looks like a straight line. Looks a lot different. There is no necessarily point of continuity, but if we were to still plug in 3, we would have 3 minus 3 up top over 3 minus 3 on the bottom, and that's equal to 0 divided by 0. Even though we have that 0 up top, we still can't divide by 0 on bottom, so it would still be undefined. So what that looks like on our graph is if you click and kind of scroll towards 3, you'll notice, all right, we get x and y values, x and y values, x and y values, and right when I hit 3, our graph says undefined. Desmos doesn't do a good job of showing holes, but it does calculate that there is a hole there. An easier method of kind of checking that is once you inspect it, say, okay, I think there's a hole at 3 because there's a matching denominator and numerator factor. I can throw that table in. I can add an x value of 3 to it to see what my graph looks like. And you'll see that it shows undefined there, so we do have a hole at that location. So we have at x equals 3, there is a hole. Now, in example 7, we can look at this and say, all right, there is something going on at x minus 5 and something else going on at x plus 1. Now let's key off. X values where the denominator of the function is equal to 0 and that same factor exists in the numerator. And if we look here, that x plus 1 exists in the numerator as well. So we have a hole at x equals -1. And actually that purple factor, that x minus 5, that is going to be an asymptote. And let's throw this in and check it out. So if we have x plus 1, and then on bottom we have x plus 1 times x minus 5, we can look and see that indeed at this x minus 5 here, we do have that vertical asymptote. Okay, and at x plus 1, which would be x equals negative 1, we're kind of expecting to have a hole right here. Let's throw a question mark in there for now to see. If we click and drag along our graph, we'll notice that right when we hit negative 1, our graph is undefined. And if we were to add a quick table to our graph and then go to the x value of negative 1, we'll also notice that, hey, our function is undefined there. So indeed, we have a hole. All right, last one we're going to do, and you'll notice that example 9 I accidentally duplicated, and that's all right. We don't need it because we got practice with this with our factored as well. We can also just use Desmos to guess and check and find any points of discontinuity or holes. If we're given this function which isn't in factored form, we have example 8 here, we can simply plug it in. We have our some fraction. Up top we have 3x minus 9. On bottom we have 4x minus 12. Okay. This is another one where we're given like kind of a straight line. If we, excuse me, if we look at it, we might just kind of have to guess and check. We can kind of click and drag along and search for a spot where maybe our graph becomes undefined. And it looks like nothing on the negative side, nothing on the positive side. Might have glanced over it. Let me go slower at this point. If we look here at x equals 3, it is undefined there. And this is something that you're normally going to get some multiple choice options with, so you don't have to guess and check blindly. But a kind of a quick way to guess and check too is to maybe build this chart up and say, hey, okay, at x equals 3, do I have a hole? At x equals 4, do I have a hole? Do I have a hole at x equals 5? You can keep going and going and going and guessing and checking, but you're ultimately looking for that undefined portion. Do not worry, you're only going to get those instances when we have multiple choice problems. But from the graph, x equals 3 is where we have a hole.